Okay, I'm going to briefly talk about how to uh, describe some regions in spherical coordinates, because this can help you do things like calculate volumes. You might have some center of masses problems or centroids, and usually you'll be given some E region, and it might not be transparent, so it's unclear what it looks like in spherical coordinates. But it turns out it's actually easier to do in spherical, so I'm just going to give you some practice. And you can also think about some of these integral problems where you're integrating over v. Remember, f equals 1 is just volume. And it's just, if you have a volume problem, it's really similar to setting up an integral. So let's just talk about how to write some of these regions that you might see on the homework. If you have a solid E above the cone z equals square root of x squared plus y squared, and below the sphere x squared plus y squared plus z squared equals 9, for example. And when you see x squared plus y squared next to a z, you should immediately think spherical. So what you can start doing is write in terms of r, and then plot using the RZ plane. RZ plane is probably my favorite coordinates to plot in. So for example, the first is z equals r, the second is r squared plus z squared equals 9. So if I plot it, z is function of r, the first curve is just this line, and the second curve is just this circle. And it's above z equals r and below the sphere, so I'm just going to draw an arrow to indicate where the region is. And really, these will be limits for your integration. So this also tells you what order of integration you might do. So this is right now we're in cylindrical coordinates. So to do spherical, it's actually simpler. And you should be clued in because there's a sphere involved, so probably spherical coordinates is the simplest way, because remember, this 9 minus r squared is actually kind of a messy thing to integrate. So, right, just think of doing the 1D integral, 9 minus r squared dr, and you get a headache. So that should immediately tell you spherical. So, in spherical coordinates, what we have now is z equals r going to rho cosine phi. I'm going to draw a phi where it should be, and I'm going to put a rho. And the right-hand side will then be rho sine phi. Oh, I'm sorry, let me just put that phi in its own diagram, not to get these things confused. Z r phi rho. Okay. Now, in the second one, the sphere, it's just rho equals 3. Right? So, and in the first one, if we cancel the rows, we get phi equals pi over 4. So, the green curve is then rho equals 3. And the red curve is then phi equals pi over 4. Okay, so we've simplified the limits. And now we just need ranges for the volume. So to describe the region, use the arrow to see where rho ranges from. It will be from 0 to 3, right? It won't be from 3 to infinity or whatever, because it has to, because remember, our diagram includes the origin. Okay, so rho goes from 0 to 3, and we also know that the angle phi is fixed. It's just pi over 4, at least on that boundary. In general, it also includes 0, right, because our region contains the z-axis. So our phi will range from 0 to pi over 4. I'm just going to quickly redraw some of this on a new page. And our region is everything in between these curves. So rho goes from 0 to 3. I'm going to redraw my arrow to indicate the rho. This will help me if I end up doing integrals to show you what my inner integration variable should be. So typically, rho will be the inner integration variable. Our phi ranges from 0 to pi over 4, and our theta is anything. 0 to 2 pi, because no equations involved theta, right? It was just r, you had r squared and you had z's. So there was no theta. Everything is cylindrical. Okay, so this is our region E. Okay, so let's do another example. Let's say E is bounded by the xz plane and the hemispheres y equals the square root of 1 minus x squared minus z squared, and y equals 4 minus x squared minus z squared. Okay, so alarm bells should go off because now we have everything's mixed up, right? Because y is what we solved for instead of z. And we were using the xz plane instead of the xy plane that we're more familiar with. So I'm going to do something possibly atypical, and I'm just going to tell you switch y and z and just rewrite the problem. Then switch back when you're done. If it's needed. So for example, if need the centroids or center of masses, just do just do it for the switch, and then just plug those numbers in at the end, and switch back at the end. Just no need to make life more complicated by trying to visualize things in the wrong plane. So it's just hard to visualize as is. So if you do the switch, so E is now bounded by the xy plane and the hemispheres z equals 1 minus x squared minus y squared, and z equals 4 minus x squared minus y squared. So this is much more familiar, and it's just easier to work with this way. So again, if you see the x squared minus y squareds and the z, I would just think spherical coordinates. It's possibly a simpler way to go about than cylindrical, and I think it's clinched by the square root. So square root equals spherical. If there's any ambiguity about whether you use spherical or cylindrical, just look for a square root. Square root is awful in cylindrical. So the one missing thing is this xy plane. Now we know this is just z equals 0. So now z equals 0, z equals 1 minus r squared, z equals 4 minus r squared. What I'm going to do next is plot this in the RZ plane. Again, what we're trying to do is get it in spherical coordinates, but I think the intuition is much better if we at least have a visualization. So in the RZ plane, and I'm just going to rewrite really quickly what our boundaries are. Well, if we plot this in the RZ plane, it's a circle of radius 1 and a circle of radius 2. And it's bounded by all of these curves. And I'm just going to also indicate z equals 0. So if it's bounded by all these curves, it has to be this annulus, or the region in between these concentric circles. And I think it's also useful to plot the xy plane, just to not totally forget about it. And really what's going on here is your theta can be anything. So theta is just anything. So you can imagine just rotating this, but you don't have to indicate this in the RZ diagram, as long as you just keep that theta in mind, that really this is a rotation. So what I would then observe is that because you have these square roots, it's easier to do this in spherical. So in spherical, if I label these 1, 2, and 3, let's skip 1. And because 2 is just clearly rho equals 1, and 3 is just clearly rho equals 2. So now for 1, this is rho. Remember, if you draw these diagrams out, you won't get confused. So z is rho cosine phi, and that is 0. So that means cosine phi equals 0. So that means phi equals pi over 2. We could have seen this also just looking at the ZR plane. So phi equals pi over 2. If I just quickly redraw this, and don't be afraid to redraw this, it just takes a few seconds and you get less clutter. So phi equals pi over 2, phi equals 0 is above, and rho equals 1, rho equals 2. So these are all of our boundaries. I'm going to indicate arrows in this coordinate system to see what I might integrate along. So you can see that now the ranges for E are rho going from 1 to 2, phi going from 0 to pi over 2, and theta, if we think back all the way, we see that 0 to 2 pi anything is okay. So this is the description of E in spherical coordinates. And you can see it's a lot better than our previous representation because we had square roots. Okay, let me just do one more example, which is kind of complicated to think about, but it's actually really interesting. The torus, rho equals sine of phi. So when you think torus, you think usually of a donut, right? And you don't really think rho equals sine of phi. So how do you convince yourself this is a donut? Well, I would actually try to write this in cylindrical coordinates, just to write in cylindrical for the purposes of plotting. I would integrate in spherical. And why are we plotting? We're plotting to get ranges for the coordinates. So if we write this in cylindrical, what we do is I would first multiply by rho squared, because that means we don't have to deal with square roots anymore. So rho squared equals rho sine phi. This is r squared plus z squared on the left-hand side. And the right-hand side, if we go back to, always draw this diagram if you don't remember. So z, r, phi, it's the polar axis, polar angle, and rho. Rho sine phi equals r. So r squared plus z squared equals r. Now what I'm going to do is rearrange this and notice that this is a quadratic, and we just complete the square. So this is 1/2 times 2. So really 1/2 r is what we're completing. So r minus 1/2 squared plus, minus 1/4, right? Because if we FOIL this out, this is r squared minus r plus 1/4. So now we need to cancel that 1/4. So we have z squared plus this thing minus 1/4 equals 0. So really what's going on, this is z squared plus a shifted radius equals 1/2 squared. So the center, this is a circle, right? So the center is at rz equals 1/2, 0, and the radius is 1/2. So I'm going to plot this now. Here is 1/2, and our circle of radius 1/2 centered at 1/2 will look like this. Okay, so we've seen that this strange looking radius is actually a circle, and this is only in the RZ plane. If you now account for the thetas, you'll notice that anything from 0 to 2 pi is okay. So really, now we have to revolve this around the z-axis, and it's full. So you revolve this fully around the z-axis, and that's how we get a donut. It's a donut that has no middle. The middle is just a single point. So it's a donut with middle equal to a point. Okay? And this is the way to visualize this in the spherical coordinate, or rather a cylindrical coordinate representation. So now if you're integrating this thing along spherical coordinates, or I guess cylindrical is probably okay, but I think spherical is probably better. If you draw your arrow, you see that anything from the origin, we go from the origin to this curve. That's our radius, and right. So this should help you see why it's a torus, at least. Okay, thanks for watching.